Okay, so hi everybody, welcome back. Today what we're going to be doing is continuing with our lecture on heat and the first law of thermodynamics. And we're going to pick up right where we left off. And so the next thing to talk about are some important relationships for molar specific heats. So there are three equations here that I want to derive for you and explain how they work. But first, let's just state what the equations are. So first, we have delta E internal is equal to N times CV. Remember, that's the specific heat for constant volume times delta T. This equation is true for any ideal gas process. So it doesn't matter how the process is carried out. We can calculate the internal energy change from this equation. Okay, the next thing is that if we have a monatomic ideal gas, so that means our gas consists of single atoms. For example, helium. If you have a helium gas, you basically just have a bunch of helium atoms flying around. Something that wouldn't be monatomic because it has multiple atoms in the molecules would be something like, CO or CO2. So strictly speaking here, we're talking about monatomic gases. But if we're talking about monatomic gases, then CV, that's our molar specific heat for constant volume. That's equal to 3/2 times R, where R is the ideal gas constant. Okay, the next relationship is CP is equal to CV plus R. And this is true for any kind of ideal gas, so it doesn't have to be monatomic. So R is the ideal gas constant. It appears in the ideal gas law. And the value is 8.314 joules per Kelvin mole. If we actually work out CV by plugging that in, and again, this will only apply to a monatomic gas, we'll get 12.5 joules per Kelvin mole. And then if we plug that in to find CP, we'll find it comes out to 20.8 joules per Kelvin mole. Okay, so there are a lot of results here. Let's see how they are derived and where they come from. All right, so the first thing that we'll do, if we want to derive those relationships, is to consider a constant volume process. And one thing that I hope you remember from last time is that if the volume is not changing, if delta V is equal to 0, that automatically implies that there's no work being done. Work is equal to 0. So then if we use the first law, which says that Q is equal to W plus delta E internal, then this is what we'll get. Since we have a constant volume process, we can write the heat as NCV times delta T. The work is 0, and then delta E internal, I'll just leave that alone. So the result of this is that delta E internal is NCV delta T. That's the internal energy change for this constant volume process. But the thing is, internal energy is a state variable. State variable. So it actually doesn't depend on the type of process that's being carried out. In fact, this relationship is generally true. Okay? It applies to any type of process. Okay. The next thing we'll bring up is the kinetic theory of gases. There was an important relationship that we derived from the kinetic theory of gases, and it was that the average kinetic energy of the molecules in a gas is equal to 3/2 Boltzmann's constant times temperature. Okay, so to be really careful with how we're saying this, what this technically is telling us, on the left side we have average translational kinetic energy of the molecules. Of the gas molecules, meaning it's just the kinetic energy associated with a molecule moving from point A to point B. If there's like a rotation going on, or like the the molecule is vibrating in some way, anything other than just translational motion, that's not included in here. Okay, so we're just talking about translational motion where a molecule moves from point A to point B like this, okay? Now with that said, internal energy is the total energy that those randomly moving gas molecules have. So how could we calculate that? Well, we could say that it's the number of gas molecules we have times the energy per molecule. Okay? And if our gas is monatomic, so here's what we mean by that. The gas is a single atom, like this, and it's not a complex molecule that consists of many atoms. That's not what we're talking about. If it's monatomic, the only type of energy the molecules have is the translational kinetic energy. I'll just write that as Ke. Because all they can do is just translate around. There's no sense in which they can rotate or vibrate or anything like that. They're just little points. So that means our internal energy is going to be given by N times that average kinetic energy that we wrote down earlier. In other words, it's going to be N times 3/2 Boltzmann's constant times time. So 3/2 NKT. Remember from the ideal gas law, this is just kind of a side note, that PV equals, I can write it as NKT, or I can write it as little n RT. So for our purposes, I want to write this as internal energy equals 3/2 little n times RT, because again, that's the same as big N times KT. Okay, so what can we do with that? Well, basically we have these two different expressions for internal energy that we've derived so far, right? One of them is right up here, and I'll write it out. It's so here, two expressions for internal energy. One of those is NCV delta T. That's the first one we came up with up here. And the other one is down here, 3/2 NR. And if we're talking about a change, we write delta T. Okay? So let's cancel some stuff. N goes away. Delta T goes away. And we're left with CV equals 3/2 times R. So that's a formula for the specific heat for constant volume process. But it only applies when we have a monatomic gas, because that's what we assumed over here when we did this derivation. So, okay, so we proved the first two results that we wanted to prove. All right, so the next thing we'll do here, and we want to prove that third result, is we'll consider a constant pressure process. Okay, so how about we start with the work? Remember that work as a gas expands or contracts is given by P dV integral. And in this case, pressure is a constant. So what we can do is we can pull it out of the integral. Now again, you can't always do this. You can only do this when pressure is constant, but since that's the case here, we can pull it out of the integral. And so what we have is just constant P times the integral of dV, which goes from, let's say, V initial to V final, okay? Those would be the limits for volume. Well, that just integrates to V, and we take it from V initial to V final in the limits, which gives us P times V final minus V initial. Another way of writing that would just be P times delta V. Because, of course, V final minus V initial is the same as saying delta V. So that's how we can calculate the work in a constant pressure process. But we can continue on with this. How about we look at the ideal gas law? PV equals nRT. Let's rearrange this to say that V, so we'll solve for V, is nRT divided by P, right? You can do that. Or if we write it in another way, we can say, let's say there's a constant nR divided by P out front. And we know this is a constant because N, the number of moles of gas, is constant. R is always a constant. And then in this case, pressure is held constant. So that whole thing is one big constant. And then we have temperature out front. So the point is, in a constant pressure process, the volume V is directly proportional to the temperature. That's what that's saying. So therefore, if we have a change in volume delta V, that's going to be that same constant nR divided by P times delta T. Because again, they're just directly proportional. You can just put it that simply. So when it comes to the work, which we said is P delta V, how about we replace that by, we replace the delta V by nR divided by P times delta T, just straight from here, and cancel out the pressure. So the work in a constant pressure process is nR delta T. It can be written that way just by making those substitutions I showed you. Okay, so what can we do with this next? We can bring in the first law once again, which states that Q is equal to W plus delta E internal. And we have a bunch of substitutions we can make. So for Q, since we're dealing with a constant pressure process, this is given by NCP delta T. The work we just found is given by N times R times delta T. And then finally, delta E internal, we worked that out earlier. We can write that as NCV times delta T. That's this expression. So we can use that right here, NCV delta T. Okay, so notice that N can be canceled out, as can the delta T. And actually, we're left with a very simple expression. CP is equal to CV plus R. That's the third result that we wanted to derive. So now, let's say we have a monatomic gas. Okay, we know that CV in that case would be 3/2 times R. We just derived that. So if we plug in the value of R, which is 8.314 joules per Kelvin mole, what we're going to find is that this works out to about 12.5 joules per Kelvin mole. So any monatomic gas has that exact specific heat when you have a constant volume process. And then CP is CV plus R, as we just derived. And if we're dealing with a monatomic gas, CV is 3/2 R, and then we're going to add R to that, so it's 5/2 R. And then we'll have 5/2 times 8.314 joules per Kelvin mole. And if you work that out, you'll get about 20.8 joules per Kelvin mole. So if we have a monatomic ideal gas, the specific heat for a constant pressure process will be 20.8 joules per Kelvin mole. Okay, so let's take a look at an example where we start using these molar specific heats in our calculations. So we have a sealed vessel which contains an unknown quantity of a monatomic gas. The vessel is rigid, which keeps the volume of the gas inside constant. The initial temperature of the gas is 245 degrees Celsius. The vessel is placed in thermal contact with the cold environment so that 1,450 joules of heat is transferred away from the gas. After this, the final temperature of the gas is 105 degrees Celsius. How many moles of gas are in the container and how many particles of gas are in the container? That's what we want to figure out. So let's do that. Okay, so we're dealing with a constant volume process here. The reason for that is the gas is in a container that's rigid, so the gas can't expand or contract. It's just kept in a constant volume. And so heat in this sort of situation, Q is given by N CV delta T. And as kind of a side note, let's talk about temperature changes. And remember that if we're going from the Kelvin to the Celsius scale or vice versa, there's a conversion where the temperature in Kelvin is given by the temperature in degrees Celsius plus 273. Okay, so what if we're talking about not a temperature, but a change in temperature? Okay, so if there's a change in temperature, and let's say we want to measure that in Kelvin, that would be T final measured in Kelvin minus T initial also measured in Kelvin. But for each of those, the T final and T initial, we can use our conversion. We can say that, okay, well, T final measured in Kelvin would be T final in degrees Celsius plus 273. And our T initial in Kelvin could be written as T initial in degrees Celsius plus 273. So notice that the factors of 273 just cancel each other out because one's positive, the other's negative. And we get T final in degrees Celsius minus T initial in degrees Celsius, which we could say is delta T in degrees Celsius. So look where we started. We had delta T in Kelvin. We end up with delta T in degrees Celsius. That means temperature changes, temp changes, are the same in Kelvin or degrees Celsius. But it's only for temperature changes that we can say Kelvin and Celsius are equivalent. If we're dealing with an absolute amount of temperature, then you can't treat them as equivalent. But for temperature changes, they are. So with that said, back to the problem. What's the heat added to the gas in this case? Well, what we have is minus 1,450 joules because the heat is flowing out of the system in this case. So the heat would be negative. N is what we're trying to find. We want to know how much gas there is. And CV, as we worked out, if we have a monatomic gas, is 12.5 joules per Kelvin mole. And then what's our delta T? Well, we start off at 245 degrees Celsius, and we end up at 105. So the change is 105 minus 245. And technically that's in degrees Celsius, but of course we just proved that a temperature change is the same in Celsius as it is in Kelvin, so we can just say Kelvin. Therefore, the number of moles, N, is minus 1,450. And then we're dividing out 12.5, and the temperature change, again, 105 minus 245. And by the way, there's some unit cancellation. Joules cancels here and here. Kelvin cancels here and here. And what we're left with is moles. So this works out to about 0.8286 mole, but we have to round to 3 sig figs. So we'll say 0.829 mole. That's how much gas we have. But if we want to convert that to a number of particles, which would be capital N, we use lowercase n for the number of moles, and we use capital N for the number of particles. This is basically a unit conversion. We have 0.8286 mole. And we use Avogadro's number to convert that to a number of particles, because by definition, every mole has 6.022 times 10 to the 23rd particles. So what does that work out to? About 4.989 10 to the 23, or to 3 sig figs, 4.99 10 to the 23. So that's how many particles or atoms that we have. Okay. So at this point, we should take a step back and try to summarize everything we've learned so far, dealing with the first law of thermodynamics applied to an ideal gas. So the equation that we started with is Q is equal to W plus delta E internal. That's the first law of thermodynamics applied to an ideal gas. And there are three variables in this equation, and we've spent a lot of the last two lectures just sort of going over how to deal with each one of these variables. So to remind you, Q, that's the heat transferred to the gas from the environment. W is the work done by the gas on its environment. And then delta E internal is the change in internal energy of that gas. So we have these three different variables. And if we start with Q, we know that if we're dealing with a constant volume or constant pressure process, we automatically have a formula for Q. In the case of constant volume, it's NCV delta T. Constant pressure, it's NCP delta T, where N is the number of moles. Delta T is the temperature change, and these are what we call our molar specific heats, CV and CP. Okay. How do we understand conceptually the sign of Q? Well, Q is going to be positive if heat flows into the system, and Q is going to be negative whenever heat flows out. And that makes sense because if delta T is positive, that means the temperature has gone up. That means Q must also be positive. That corresponds to heat flowing in. If delta T is negative, the temperature is going down, then Q is negative. So the sign should make sense intuitively. What about work? Well, if we have a quasi-static process, which means we carry out the process very, very slowly, we can calculate the work as the integral of P dV. Okay? And by the way, in this class, we're only going to be using or thinking about quasi-static processes. So this will always apply. Now, the way you interpret the sign of W is if the gas is expanding and the volume is increasing, then W is positive. If the gas is contracting, meaning it's shrinking into a smaller volume, then W is negative. That just pops right out of the definition. Now, for any process whatsoever, we can say that delta E internal, change in internal energy of the gas, is given by NCV delta T. So again, if we think about the sign of this, if delta E internal is positive, that's telling us temperature is rising. If delta E internal is negative, that's telling us the temperature is dropping. So that's kind of a summary of everything that we've derived so far. So it's good to just see it all in one place before we move on. Okay, the next thing we'll do is talk about ideal gas processes. Okay, so when it comes to ideal gas processes, we're just talking about different ways a gas can undergo a change, okay? And there are many different things you could think of for how a gas could be maybe expanding or contracting. Maybe the pressure is increasing, maybe the temperature is increasing. There are all kinds of things you could think of, but there are four processes that we're going to focus on in this class. So you really need to know these four very well, but we're not really going to look beyond these four. And these four are important because A, they're very simple to describe mathematically compared to other things. And B, they're important theoretically. Once we get to chapter 20, you'll see how these keep popping up. So the first one is an isochoric process. This is a process that occurs at constant volume. So delta V, the change in volume throughout the process, is 0. That's the defining feature of isochoric. Sometimes you might see this referred to as isovolumetric. It means the same thing. Volume is not changing. Okay, the next one is isobaric. This means that the gas is maintaining a constant pressure. So delta P, the change in pressure, is equal to 0. Okay, the next one, isothermal. This means that the gas is maintaining a constant temperature. So throughout the process, delta T is equal to 0. And then finally, adiabatic. An adiabatic process is any process that occurs with no heat transferred to the gas from the environment. So it means Q is equal to 0. No heat is flowing in or out of the gas during the process. So what we're going to do is really study these 4 processes in depth, and we're going to derive expressions for the work, for the heat, and for the internal energy change. Those are all the variables that appear in our first law equation for each of those processes. And we're going to come up with these expressions in terms of pressure and volume. So that'll be our task for the next section here, is to come up with those expressions, W, Q, and delta E internal for each one of these processes. Okay, so let's start with an isochoric process. This is, again, a process that occurs at constant volume. So on the PV diagram, what you should be picturing is we start at some initial state over here, and we end up at some final state, but those 2 states have the same volume. So the volume is held constant throughout. So what this looks like is just a vertical line on the PV diagram, starting at some pressure and ending at some other pressure. So let's take a look, based on this, at what the expression for the heat, the work, and the internal energy change is going to be for an isochoric process. Okay, so let's start with work. Remember that work, W, done by a gas, is given by P dV. But in this case, we have no volume change. So immediately we know that there's no work being done. That's always the case in an isochoric process. The next thing we can look at is the first law, which says Q is equal to W plus delta E internal. That's the first law of thermodynamics applied to an ideal gas. And since we have 0 work, plug in 0 for W, Q is equal to 0 plus delta E internal, i.e., whatever heat gets added to the gas just contributes to the internal energy of the gas. In other words, any heat that gets added increases the internal energy of the gas. Any heat that gets taken away, it decreases the internal energy of the gas. That's what this is telling you. Okay, and then lastly, let's look at the ideal gas law, which states PV equals nRT. And we can rearrange this to solve for the temperature. Temperature is equal to V divided by nR times P. That's how we can rearrange the equation. And what I want to do is circle these constants right here, because V, which is the volume, N, the number of moles, and R, the ideal gas constant, these are all constants. So that's just one big constant. In other words, the temperature is directly proportional to the pressure when we have a constant volume process. So delta T is just going to be that same constant, V divided by nR, times delta P. The next thing we'll do is remember that delta E internal for any process whatsoever can be written as N CV delta T. And if we plug in what we just worked out for delta T, we have N CV, V divided by nR, times delta P will cancel out N. And what we'll be left with is CV divided by R times volume, and again, the volume is constant, times delta P. So what we've just worked out is the work, the heat, and the internal energy change in a constant volume process, and everything is expressed in terms of pressure and volume changes. Okay, so here are the results. Again, I just want to write down the first law equation, which says Q is equal to W plus delta E internal. It's really important for every type of process that we go through to know how to deal with each one of these variables. And so what we did is we came up with expressions for each one of those variables. Work is equal to 0. Delta E internal is equal to CV divided by R times V delta P. And then Q is just the same exact thing as delta E internal in this case. So what we have to say about a constant volume process is that no work is done, and all of the heat transferred to the gas goes into changing the internal energy of the gas. Okay, next, let's look at isobaric processes. So this time, the process occurs at constant pressure. So on a PV diagram, this is what it will look like. We have an initial state over here, and in order to get to the final state, we have to keep the pressure constant. So that means we're going to follow a horizontal line where the pressure stays the same to get from initial to final. So in that process, the volume will be changing, but the pressure will be staying the same. So let's work out, again, the expressions for work, heat, and internal energy for this type of process. Okay, so now we're dealing with a constant pressure process. And let's start with work. Okay, work is given by the integral of P dV, as usual. But if pressure is constant, then it's something that can be pulled out of the integral. So we have P out front, and then we have the integral of dV, and we should really be putting limits on this thing. We go from V initial to V final, whatever those two volumes happen to be. Now, of course, when we integrate dV, we just get V, and we evaluate that from V initial to V final. So what we'll have is P times V final minus V initial. And a more compact way of writing that is P times delta V, because of course, V final minus V initial is just delta V, the change in volume. So as long as we have constant pressure, that's how we express the work. Okay, the next thing I'd like to do is take a look at the ideal gas law. Okay, and again, the ideal gas law says PV equals nRT. So if we go ahead and solve for the temperature, just like we did before, we can write it as P divided by nR times V. All right? Now, if I circle this part of the expression, P divided by nR, well, pressure is constant, N is constant, and R is also constant, so that's just one big constant. And what that means is delta T, the change in temperature, can be written as P divided by nR times delta V. Because again, temperature and volume are going to be directly proportional to one another if you're holding the pressure constant. So we know that the heat in this type of process is given by NCP delta T, because again, pressure is constant. We want to use the specific heat for constant pressure. And that's a perfectly fine expression, but what we're trying to do here is express everything in terms of pressure and volume, because those are things you can read off of a PV diagram. So instead of delta T, we'll sub that in for P divided by nR times delta V. That's what we just worked out over here. And N is going to cancel. And what we'll be left with is Cp divided by R times P delta V. Okay, so that's an expression for the heat in this type of process. So the last thing we can do is come up with an expression for the internal energy change, delta E internal. And we'll remember that regardless of what type of process we're dealing with, we can always write this as N times CV times delta T. And we're going to make that same substitution that we just made for delta T. We have NCV times P over NR delta V. So again, I'm subbing this guy in. And just like before, N is going to cancel. And we'll be left with CV divided by R times P times delta V. So what have we just done? We've worked out an expression for the work, an expression for the heat, and an expression for the internal energy change in a constant pressure process. And we made sure that it was expressed entirely in terms of pressure and volume so that we can use a PV diagram to calculate everything. Okay, so let's take a look at what we found. Again, we have expressions for Q, which is the heat, W, which is the work, and delta E internal. We found that Q is equal to Cp divided by R times P times delta V. We found that the work is equal to P times delta V. And we also found that delta E internal is equal to Cv divided by R times P delta V. So these are what are valid for a constant pressure process. So the way you can think about this conceptually is that if we add some heat to the gas at constant pressure, it can go two places. Some of it goes into work, so that would be expanding or contracting the gas. And then some of it goes into changing the internal energy of the gas. It goes both places. Okay. The next process that we want to take a look at is the isothermal process. So isothermal means temperature is staying the same throughout the process. So before we get into the equations that describe this, we want to take a closer look conceptually at how would you actually carry out an isothermal process. Because the idea would be, I want to think of some way that we could take a gas and have it expand or maybe contract, all while keeping the temperature constant. So the picture you should have in mind is something like this. We have a gas inside of a cylinder, and that gas is in thermal equilibrium with something that we call a heat bath. So a heat bath, for our purposes, is just a system that is so big that the temperature doesn't really change, even if heat flows into or out of it. So in other words, it's just some really, really big system that even if a little heat flows out of the gas and into that system, or the other way, some heat flows into the gas from the system is so big that the temperature is really not going to change by any significant amount. Okay, so the next thing that we want to sort of imagine in this picture is that there is some mass sitting on top of the piston. And the mass is divided up into little tiny increments. If you want to imagine something more concrete, maybe imagine this is a big pile of sand. And you can take little grains of sand off to decrease the mass, or you can put little grains of sand onto it to increase the mass. Let's imagine the gas is expanding, so we'll take mass off to get the gas to expand. And again, we're going to do this by taking little infinitesimal amounts of mass off, one at a time. Okay? If we do it that way, and we again adjust the mass in really, really tiny increments, we can get the gas to expand at a constant temperature. Or if you think about it the other way, if we add little tiny bits of mass one at a time, we can get it to compress at a constant temperature. So what we're describing here is a quasi-static process because it happens really, really slowly. And in fact, if we wanted a perfect isothermal process, it would technically take an infinite amount of time to do that. So an isothermal process, a true isothermal process, is a little bit of an idealization, right? It's not something you can really carry out in the real world, but it's still very useful. It's useful theoretically, and what we'll see in chapter 20 more about that. And even though you can't exactly carry out an isothermal process, some things are pretty close to an isothermal process. So it's a good approximation of things that happen in the real world. So anyway, point is, even though it's a little bit of an idealization, it's still a really useful concept. So what I'd like to do here is sketch out in a little bit more detail the isothermal process that I was referring to earlier. So let's draw a picture of the gas in a cylinder with a little piston on top, and there's some kind of mass resting on top of the piston. Let's call that M. And again, there's some gas in the cylinder. So this is our starting state. Right now, the gas is in equilibrium with the heat bath. And so that means they have the same temperature. The temperature of the gas and the temperature of the heat bath are the same. Also, the piston is not going to be moving in this case. Piston is stationary. But what we're going to do next is we're going to take a little bit of mass off of the piston. We're going to remove mass, and let's call it delta M. How about? We'll remove mass delta M. And so what happens next? Well, we're going to have the piston, and the mass on top of it is now going to be M minus delta M, because we've decreased the mass by that much. And so, because we've reduced the pressure pushing down on the piston is going to move up a little bit. So the piston moves up slightly. That means the gas expands. And if you think about what happens when the gas expands, the temperature should drop as well. So the temperature of the gas should drop slightly. So now what do we have? We have temperature of the gas is a little bit less than the temperature of the bath because its temperature has dropped a little bit. Okay, so next, what will be happening? Well, we have M minus delta M sitting on top of the piston. And the gas is inside of the cylinder. What happens if the temperature of the gas is less than the temperature of the heat bath? Remember, heat will flow from hot regions to cold regions. So we're going to have a little bit of heat flowing into the gas from the heat bath. That's dQ. It's a little bit of heat flow. So heat flows from the bath, the heat bath, to the gas because there's a temperature difference. But after that little heat flows, equilibrium becomes reestablished. So the equilibrium is reestablished. So after that heat flows, we have T gas equals T bath once again. So that's really the process. If you take the mass off of the piston in little bits, the gas will expand a little bit, some heat will flow into the gas from the heat bath, and then equilibrium will be reestablished. But notice that even in this picture, this is not a true isothermal process because if we look at this stage in the middle, the temperature of the gas slightly went down, so it didn't really stay constant. If we want to make this a true isothermal process where there's really no temperature change happening at all, we have to take dm, or sorry, let's say delta m, that little bit of mass we're moving each time, we have to take that to 0. We have to take the limit where delta m goes to 0 for true isothermal process. But the thing is, if the amount of mass you're taking off each time is actually 0, then it would take infinitely long. It would take infinitely long to carry out. Which is why we say this is an idealization. It's not something you would actually do in the real world, but again, it's still a useful concept. Okay, so I have a question for you guys to think about and try to work out on your own. The question is the temperature constant for the process shown in the PV diagram below? So we have, starting from this initial state, we follow this path on the PV diagram to get to this final state. So is that isothermal? Is that constant temperature? So yes, no, or not enough information. Pause the video, think about it for a bit, and see what you come up with. Okay, so how about we just start by saying the answer is no. That is not an isothermal process that we saw on the graph. And the reason we know that is, let's just write down the ideal gas law. PV equals nRT. And it's always useful in whatever process that's happening to sort of think about what's constant. Well, the number of moles is constant, N is constant, R is always constant, and then T is constant by definition. So nRT, all of that is just one big constant. In other words, PV is constant in an isothermal process. Another way of saying that is P is some constant, whatever that would be, divided by V, or P is inversely proportional to V. So how do we show on a graph, on a PV diagram, that pressure is inversely proportional to volume? Well, the graph of 1 over V looks like this. So this is the type of curve that must be followed for an isothermal process. It has to have this shape. And very clearly, the one that was shown to us doesn't have that shape. So we can say it's not isothermal. Okay, so now that we understand what an isothermal process is, we can start to come up with the formulas that are relevant to this sort of process. So on a PV diagram, we know we're dealing with a constant temperature process when it follows this type of curve, which we call an isotherm. And as we said earlier, PV is equal to a constant along this curve. That's sort of the defining feature of it. So we imagine in this process that we start at an initial state, we follow this isotherm curve to some final state. So let's work out an expression for the work, the heat, and the internal energy change for this type of process. Okay, so now we're dealing with isothermal processes. And I guess we could start with internal energy change. Remember that for any process, delta E internal is given by N CV times delta T. But the thing that distinguishes an isothermal process is that delta T is equal to 0. There is no temperature change. So therefore, there's no internal energy change. That's equal to 0. Next, we can take a look at the work. So work is given by the integral of P dV. And the way we can figure out how to approach this integral is to take a look at the ideal gas law, PV equals nRT. And again, we know that N, R, and T, at least for an isothermal process, are all constant. Okay, so in other words, we can write the pressure as nRT, which is constant, divided by V. So we'll do that. The work is given by the integral of nRT divided by V times dV. That's what we sub in for the pressure. And the next step we can take is to pull out these constants. N, R, and T are all constant. Then what we're doing is we're integrating dV over V. And let's put the limits on this. We're going from V initial to V final. So hopefully you remember how to integrate 1 over V. That integrates to the natural log of V. So we have nRT, and then we have the natural log of V. And we better evaluate that at the limits V initial to V final. By the way, in thermodynamics, this natural log popping out of an integral just happens a lot, so you'll see it definitely more than once. So we have nRT. When we plug in the top limit, we have natural log of V final. We subtract the bottom limit, which is natural log V initial. Okay, so one property of natural logs that you should get used to is the fact that if we're subtracting one natural log from another, we can actually combine that into a single natural log by division. So this is the same as natural log V final over V initial. And then as a final step, since what we want to do here is sort of express everything in terms of pressure and volume so that we can work everything out from information on a PV diagram, nRT is just PV. So we have PV times natural log V final over V initial. That's an equivalent expression. So this is the same thing. And you might be wondering, like, well, what values of P and V am I going to actually plug into that? Any values on the isotherm curve are going to work. Okay? Because again, P times V is constant along that isotherm curve. So whatever you plug in for P times V, you're going to get the same answer. Okay, so that's the expression for the work. So the last thing we'll do is we'll write down the first law as it applies to ideal gases, which says Q is equal to W plus delta E internal. And in this case, Q is equal to W plus 0, because remember, there isn't any internal energy change happening. That's equal to 0. So Q is equal to W. So it's the same exact expression for the work. That's also the heat. And so here's what we have. Again, look at the first law. We have Q is equal to W plus delta E internal. We can break that down into the 3 different variables. When we have an isothermal process, there's no internal energy change. The work is given by PV times ln V final over V initial. And Q, the heat, is just equal to the work. So you can use that same expression that we derived for work to calculate the heat. So what we find is internal energy doesn't change, and all the heat that's transferred to the gas, therefore, goes into performing work. So Q is equal to W, in other words. All right, so up until this point, we've covered isobaric processes. Those are constant pressure processes. Isochoric, that's constant volume. And isothermal, that's constant temperature. There's one more that we haven't looked at yet, which is adiabatic. We're not quite ready to get there yet. So let's do an example using everything that we've derived. And here's what we're doing. A monatomic ideal gas undergoes the cycle shown in the PV diagram. Calculate the work done in each process. In one full cycle, how much work does the gas do? We're going to calculate that in joules. Then, if the system completes 36 cycles per minute, what is the power output in units of watts? So there's a conversion factor that we're going to use here, and I'll explain where this comes from as we do the problem. But the conversion factor is 1 atmosphere times a liter is equivalent to 101.33 joules. Okay? So what's going on here is we start the process at point A. We follow this isothermal curve to point B. So the gas is expanding Volume is increasing, but the temperature is staying constant until we get to point B. Then what happens is we follow the curve to point C. This is isobaric because the pressure is staying the same. And then we're compressing the gas back to a smaller volume. Then we're keeping the volume constant, and we're increasing the pressure until we get back to point A. So that's a cycle, and we can just keep doing that cycle over and over again. And that's what it means to say the system completes 36 cycles every minute. So every minute, it just undergoes that cycle 36 times. Okay, so let's start with the isothermal process, which again takes us from point A on the diagram to point B. And we have an expression for the work, which is PV times the natural log of the final volume over the initial volume. So the final is at point B, so I'll write that as VB. And the initial is at point A, so I'll write that volume as VA. Now, as far as the PV that appears at the front of the expression, again, we can pick any point along this isothermal curve. So let's just say point A. So PAVA, that'll work. Okay, so for the pressure at point A, it's 5 atmospheres, 5 atm. The volume is 2 liters. And then we have the natural log of, okay, the volume at point B is 10 liters. Volume at point A is 2 liters. So that's the ratio. So the units that you get out of this are actually atmospheres times liters. And the numerical value is 16.1. Okay, so next, we'll look at the isobaric process. That takes us from point B to point C. And we found that the work in a process like this can be expressed as P delta V. We derived that. So what is the volume change? Well, at the end of the process, we end up at point C. And at the beginning, we're at point B. So VC minus VB is how we would think about the volume change in this case. And the pressure is just constant. So here's what we have. We have a pressure of 1 atmosphere. And then we have VC is equal to 2 liters. And VB is equal to 10 liters. So you calculate that and you get negative 8 atmosphere liters. Okay, then we'll do isochoric, which takes us from point C to point A. So back to where we started now. But this one is super easy because the work is just 0, right? If there's no volume change, we learned that there is no work being done by the gas. So here, let's actually label these a little better. Isothermal, we can call that work WAB. Isobaric, we can call that work WBC. And then isochoric, we can call that WCA, because those are the points along the diagram that we're following. So for the whole cycle, complete cycle, the total work, well, that's equal to WAB along the isothermal curve plus WBC, isobaric, plus WCA for the isochoric. And what we have is 16.1 atmosphere liters minus 8.0 atmosphere liters and then plus 0. So the total work done by the gas for one cycle is 8.1 atmosphere liters. So in one cycle, the gas is actually doing some work. And to kind of give you a hint as to where we're going in chapter 20, we're going to start talking about engines, heat engines. So if you can get a gas to do work in a cycle like this, that's pretty much what's going on inside the engine of your car. We'll talk a lot more about that in chapter 20, but this is a little bit of a hint to that. Okay, so we want to convert the units to joules at the end of this. So remember, 1 atmosphere liter is equivalent to 101.33 joules. Cancel out atmosphere liters. And this works out to about 820 joules. So in one cycle, you get 820 joules of work that the gas is doing. So why don't we take a look at the units? So we'll start with atmospheres times liters. And we'll remember that in 1 atmosphere of pressure, we have 1.0133 10 to the 5 pascals. Okay? And we'll also remember that a pascal is the same as a joule per cubic meter. And let's try to cancel some things out. Atmospheres go away, pascals go away. Okay, so there's one more thing we want to do, which is to say that in every cubic meter, we have 1,000 liters. So liters on the bottom cancels with liters over here. Meters cubed cancels with meters cubed, and then we're just left with joules. And if you do that calculation, you'll find it's 101.33 joules. So atmospheres times liters is actually a unit of energy, and it's equivalent to 101.33 joules. Okay, the last thing we want to do here is calculate the power. Okay, so here, power output. So we want the units at the end of the day to be watts. So we want units of watts. Okay, and remember also that a watt is a joule per second. So we'll start with what we know. We have 820 joules of energy for every time the gas undergoes the cycle that we see in the diagram. So we can say 820 joules per cycle is the rate at which our gas is doing work. But if we multiply that by 36 cycles per minute, which is what we were given in the problem, we'll notice that cycles cancels out both here and here. Okay, so now the units we have are joules per minute. That's pretty close to what we want. We want joules per second. The only thing we have to do is say that in every 1 minute, there are 60 seconds. And now the units are joules per second, just like we want. So if you work that out, you're going to get about 492, keep 2 sig figs, joules per second, which is about 490 watts. So what we're seeing in this diagram is actually an engine that has a power output of 490 watts. Okay, so those are the answers. For the isothermal process, we had 16.1 atmosphere liters. For the isobaric process, we had -8 atmosphere liters. No work done at all for the isochoric process, so 0. And then when you add those together to get the total for the cycle, we got 8.1 atmosphere liters, which is the same as 820 joules. And then when we calculated the power output, we got 490 watts. Okay, so that's how that problem works. And we'll actually do a continuation of that. So it's the same exact PV diagram that we were working with before. But now the question is, calculate the heat transferred to the gas in each process. And in one full cycle, how much heat is transferred to the gas. So we're going to assume that the gas is monatomic, and we'll use that same conversion factor. 1 atmosphere liter is equal to 101.33 joules. Okay, so we'll again start with the isothermal process, which again takes us from point A to point B. And we'll just use the formula we derived, that in an isothermal process, the heat is equivalent to the work that's done. And we actually calculated this. We calculated the work done by the gas going from A to B, and we found it was 16.1 atmosphere liters, so that's the same as the heat, as long as we're dealing with an isothermal process. Next, we're going to do isobaric. That's the one that takes us from point B to C on the diagram. And we're going to be dealing with the specific heats, so let's just do a kind of side note about that. CV is 3/2 times R for a monatomic gas. So again, that just means single atoms. And CP is always equal to CV plus R. So in this case, we're taking 3/2 R for CV plus R, which is 5/2 R. So that's what we're going to use. Okay, next, we're dealing with a constant pressure process, and we derived a formula for the heat, which was Cp divided by R times P times delta V. So this would be the heat for the process going from B to C. And now what we're going to do is plug in for Cp 5/2 R, and we're dividing by R, and then P times delta V, so the R cancels out. What we're getting is 5/2 times the pressure, which is 1 atmosphere the whole time, and then delta V is the volume change, so we end up at 2 liters, having started at 10 liters. So if you work this out, you get minus 20 atmosphere liters. So that means the gas is giving off 20 atmosphere liters of heat as it goes from point B to point C on the diagram. Okay, next, isochoric. So this is taking us back to point A, so going from point C to point A. And what we derived is that for an isochoric process, the heat is given by CV divided by R times V delta P. Okay, that's the formula we derived. And we'll plug in 3/2 times R for CV, and we'll divide by R. And then again, we'll have V times delta P. Cancel out R. Okay, so we have 3/2. Now the volume, as we go from C to A, is constant. It's 2 liters. That doesn't change. But the pressure change, delta P, well, we end up at 5 atmospheres, having started at 1 atmosphere. So 5 minus 1. And if you work this out, you're going to get 12 atmosphere liters. So I should be a little careful. I'll label that as QCA. So the heat transferred to the gas during that process. Okay, so we used the formulas that were derived to calculate all of these different heats. So again, if you're wondering where these formulas came from, we derived them earlier. And now we can calculate the total heat, Q total. That's QAB plus QBC plus QCA. That's the total heat transferred to the gas in one whole cycle. So we have 16.1 atmosphere liters minus 20 atmosphere liters, and then plus 12, which works out to 8.1. And that's the same as what we got before, right? When we converted the units, we got 820 joules. So a total of 820 joules are transferred to the gas in the form of heat during this process. Okay, so to summarize the results, the heat during the isothermal process was 16.1 atmosphere liters, minus 20 atmosphere liters during the isobaric process, and then 12 atmosphere liters during the isochoric process. When you add these together, you get 8.1 atmosphere liters, and that's equivalent to 820 joules. So again, just another example of how we can use the formulas we derived to make some calculations. Okay, the last thing that we'll do with this PV diagram is ask the question, in one cycle, what is the total internal energy change of the gas? So find delta E internal for the gas during one full cycle. And I'll give you three options. It's either going to be 820 joules, minus 820 joules, or 0. So try to figure this out, pause the video, and then come back to it once you think you have an answer. Okay, so there are sort of two ways to look at this. The first way you can think about this is use the first law of thermodynamics applied to an ideal gas. So this is the equation we've been working with for quite some time. And we'll apply it for one cycle. Okay, so we'll think about it for one whole cycle of this PV diagram. So Q is equal to W plus delta E internal. That's the equation we're thinking about. But we know that the heat is 820 joules for one full cycle. And also, the work is 820 joules for one full cycle. So we have plus delta E internal at the end there, but it should be clear that delta E internal is 0, meaning if we follow the system for one full cycle and we return to where we started, that there's no overall change in internal energy. And that kind of brings us to the second way of thinking about this, which is that internal energy is a state variable. So it only depends on where we are on the PV diagram. It doesn't depend on, how we got there. So delta E internal is a change, right? We can think of this as final minus initial. Well, where do we end up after one complete cycle? We end up at point A. Where did we start? Well, we started also at point A. So basically, the change in internal energy for one cycle can be thought of as the internal energy at point A minus the internal energy at point A, because again, this is final and initial. And of course, those are the same thing, right? You're just taking a number and subtracting it from itself. So you have to be getting 0. Okay, so either way you think about this, the internal energy change for a full cycle is going to be 0. Okay, so what we found is that if you follow a cycle where you end up right back where you started at the beginning, the total internal energy change is going to have to be 0. So with that said, that's the end of this video. We're going to continue on in the next video with our discussion of heat and the first law of thermodynamics. And we should be able to finish all of this lecture in the next video. So I'll see you then. Take care.